Hello, my name is Dongyun, a PhD student at Utah State University. This presentation introduces our work titled Perception of Visual Variables on Virtual World-Size Tile Displays in Immersive Environments. Immersive environments have two unique benefits over the real world for performing visual analytic tasks. The first benefit is flexibility in creating and placing virtual displays. Recently, data has grown in size and complexity, and it leads to increasing the demand for multi-display or large display setups. Immersive environments enable users to create and arrange many virtual displays within their surroundings. The second benefit is novel 3D user interactions. Users in immersive environments can do novel interactions which are unattainable in the real world, like teleportation and portal. To perform visual analytic tasks using immersive technologies, precise evaluation and comparison of visual elements are important because data is represented in graphical forms. For example, visual elements include lengths, area, and angles, and they are used in visualizations to represent data values like bar chart, bubble chart, and line chart. There were earlier research works that investigated the human perception ability using various display settings in the real world. Inspired by those earlier research works, this work aims to investigate how people accurately perceive visual variables by using a world-sized virtual display in VR. This research work is proposed to answer the following research questions. The first research question is, to what extent does the virtual display arrangement affect the user's perception of visual variables? Second, how does the accuracy of perceiving visual variables in VR differ from that in the real world? Third, how does the introduction of different VR interaction techniques affect the perception of visual variables? To answer the research questions, this study employed a psychophysical approach called size reproduction task. In the task, a stimulus and modulus are given, and participants are asked to resize the stimulus to the size of modulus. This task was conducted in VR. In VR, it looks like this. The blue item is stimulus and the red item is modulus. Users can control the size of the stimulus. This task allows us to understand how people accurately perceive visual variables by different conditions in VR. We designed two user studies. The first user study is designed to evaluate human perception ability in VR. This study is motivated by earlier research work performed in the real-world setting and follows its study setup. As a result, our first study results can be compared to those obtained in the real-world settings. The second study is designed to investigate how users' interaction techniques could help users perceive visual variables accurately. The first study adopted a mixed study design. It has 5 independent variables, and they will be introduced in the following slides. The large word display arrangement factor is a between subject vector, and the others are within subject vectors. There are 3 dependent variables to measure effectiveness of independent variables on human perception ability. They are absolute error, estimation error, and task completion time. Absolute error is the percentage difference between the perceived and target size, and estimation error evaluates the directional tendency of the perception error. This presentation focuses on reporting absolute error and task completion time. For more details about estimation error results, please refer to our paper. Independent variables. First, for the large word display arrangement factors, 3 arrangements are considered, including flat, curved, and cockpit arrangements. They are selected because of their extensive utilization in previous research. Next, for the visual variables, length, area, and angle are selected based on earlier visualization perception research. When a new task is started, they have their own initial sizes called S. There are 3 modulus conditions. Three modular sizes are 0.1, 0.4, and 0.7 times their initial stimulus sizes. For more details, please refer to our paper. There are 9 modulus locations from A1 to H4. In our analysis, results were analyzed by columns. And there are 2 stimulus locations called frontal display and personal display. The frontal display is the case where the stimulus display is one of the virtual world display and is positioned in front of a user. The personal display is the case in which the stimulus display is positioned near a user, controlled by Vibe controllers. This is a condition which is hard to achieve in the real-world settings. A total of 51 participants were recruited, and 2 of them withdrew their participation during the study due to VR sickness. From this slide, summary of Study 1 analysis results are presented. For each result, 2 charts are presented vertically. The upper chart shows the results by the conditions, and the bottom chart shows the comparison results between the conditions. In the bottom chart, if a confidence interval does not include the 0 value, it suggests that there is a clear difference between the conditions. First, results by display arrangements. The results show that cylinder and cockpit had lower absolute error than flat, but cylinder took longer task completion time than cockpit and flat display arrangement. Next, the results show that frontal had lower absolute error than personal, but it took longer task completion time than personal. For visual variables, there was no significant difference in absolute error among them. However, angle was perceived as the fadest, followed by area and length. Regarding modulus location, the results suggest that a closer modulus display leads to lower absolute error and faster completion times. The results also disclose that a smaller modulus size leads to higher absolute error and longer task completion times. And this is the summary of comparative analysis results between our VR study and earlier real-world studies results. The findings indicate a trade-off between absolute error and completion time, with the cylinder and cockpit conditions in VR showing lower absolute error but taking longer than the flat condition in the real world. Our findings from the first study results and participants' feedback are as follows. First of all, the cylinder layout showed better performance than the flat layout in terms of perception accuracy. Next, based on the frontal and personal display results, supporting users in reading 2 visual variables at comparable depths is important. Third, we found no clear evidence for perception accuracy differences between visual variables in VR. At last, VR could provide a practical virtual space using virtual displays to perform visual comparison in terms of perception accuracy. Our second study is to investigate the effectiveness of interaction techniques on perceiving visual variables. The second study adopted a within-subject study design. To conduct the study in a manageable time, the second study only utilized the flat wall and area visual variables. The second study has 3 independent variables, including interaction technique, modulus location, and stimulus location. Variables for modulus location and stimulus location are similar to the study 1. The new variable is an interaction technique, and they will be introduced in the following slide. 3 key measurements were absolute error, task completion time, and user head movement records. 4 interaction techniques are explored compared to a baseline condition. The baseline condition is called no interaction, and this is an exclusive for frontal display. This condition is selected based on our first study results, which showed lower perception error in the flat world condition. 4 interaction techniques include selection, working, steering, and teleportation. Selection is designed only for the personal display condition. By using a controller, participants can select a distant display and bring its copy to their side. Walking indicates physical walking. Participants can move around immersive environments by walking in the real world. Next, steering is a kind of virtual walking. This technique allows participants to use their non-dominant controller like a joystick to move around the VR scene. The last interaction technique is teleportation. Teleportation allows participants to promptly relocate to the specified location. This is widely used in numerous VR applications. Here are the results. The left chart shows the results by conditions, and the right chart shows their comparison results to the baseline condition of no interaction. Compared to the baseline condition, interaction improves task performance in terms of absolute error, except for teleportation with frontal condition. The baseline condition showed the fastest completion time. Overall, introduction of interaction techniques led to longer task completion times for both frontal and personal conditions. However, we found using selection with personal had no clear difference with the baseline condition. Next, we report task strategies participants showed. First, when the participants used the frontal display, we found two representative strategies called target strategy and overview strategy. Target strategy involves oscillating between stimulus and modulus positions to assess their sizes. During the target strategy, we observed an interesting user behavior of using the controller as a measurement tool. The overview strategy entails navigating toward the center area between the modulus and stimulus before assessing their sizes. When participants used the personal display, a simple user behavior was found across the interaction techniques. They brought the personal display next to the modulus and made direct comparisons. Interestingly, some participants adopted a strategy utilizing jet fighting by overlapping the stimulus and modulus to compare their sizes. Our second study showed that user perception ability can be improved with 3D user interactions. While the personal display conditions showed poor performance in the first study, we found the personal display with selection can greatly assist users in perceiving visual variables. At last, based on user movement analysis results, steering and teleportation showed similar user behaviors to walking, and this finding demonstrates their potential as alternative interaction techniques to walking. Thank you for watching.